The second half of Chapter 9 dealt with power series, Taylor and Maclaurin polynomials, and Taylor and Maclaurin series. So this is all of these stuff where we use series to approximate functions, or find series that equal functions exactly. So the first thing we discussed was how to find Maclaurin and Taylor polynomials. So this is a generalization of the idea of a tangent line approximation to a function. So a Maclaurin polynomial of degree 2 would approximate a function near 0 using a quadratic, degree 3 would use a cubic, and degree 4 is going to use a polynomial of degree 4. And just remember that a Maclaurin polynomial meant that your center was at c equals 0, and the fourth Maclaurin polynomial is given by f of 0 plus f prime of 0 times x plus the second derivative at 0 times x squared all over 2 factorial plus the third derivative evaluated at 0 times x cubed over 3 factorial, and plus the fourth derivative evaluated at 0 over 4 factorial times x to the fourth. So we're going to need to find the first 4 derivatives of e to the x, but that's not super hard. So f of x is equal to e to the 3x. The first derivative is 3e to the 3x. The second derivative is 3 squared e to the 3x. The third derivative is 3 to the third e to the 3x, and the fourth derivative is 3 to the fourth e to the 3x. So the Maclaurin polynomial, when we input 0 into the original function, we get 1. Inputting 0 into the first derivative, we get 3, so we have 1 plus 3x. Inputting the 0 into the second derivative, we'll have 3 squared over 2 factorial x squared plus inputting 0 into the third derivative, we'll have 3 to the third over 3 factorial x cubed, and lastly 3 to the fourth over 4 factorial x to the fourth. If you choose to expand those powers, if you choose to multiply or expand out the coefficients, the squareds and cubes and fourth powers and factorials, you'll end up with 1 plus 3x plus 9 halves x squared plus, once again, 9 halves x to the third, and then plus 27 eighths x to the fourth. If you're putting problems in a WebAssign, it should take either answer as long as they are equivalent. Find the Taylor polynomial of degree 3 for f of x equals 2 over x centered at c equals 1. So the Maclaurin polynomial in the previous example approximates the function e to the 3x well near the point x equals 0. This Taylor polynomial will approximate the function 2 over x near the point c equals 1. So in general, centered at c equals 1, t4 of x will be given by, degree 3 actually, so t3 of x. That will be given by f of 1 plus f prime of 1 times x minus 1 plus the second derivative at 1 over 2 factorial times x minus 1 squared plus the third derivative at 1 over 3 factorial times x minus 1 cubed. Now, before we proceed, we need to find a whole bunch of derivatives. So, first of all, f of x is the same, 2 over x is the same thing as 2x to the negative 1. So the first derivative is negative 2x to the negative second. The second derivative is positive 4x to the negative third. And the third derivative is given by negative 12x to the negative fourth. And we'll use those to find this Taylor polynomial. So inputting 1 into the original function, we'll get 2 over 1, or 2. And then minus, inputting 1 into the first derivative, we'll have negative 2 over 1, so negative 2 times x minus 1. And then plus 4 over 2 factorial x minus 1 squared. And then minus 12 over 3 factorial x minus 1 cubed. Now notice that some stuff can cancel. We'll have 2 minus 2 times x minus 1. 2 factorial is just 2. 4 divided by 2 is positive 2. And the next term, 3 factorial is 6. 12 divided by 6 is negative 2. So negative 2 x minus 1 cubed. So also the coefficients there are flip-flopping between positive and negative 2. So Maclaurin and Taylor polynomials can be used to approximate functions near where they are centered. So they're most accurate there. And we had this Taylor's inequality that the absolute value of the remainder was less than or equal to the absolute value of x minus c to the n plus first all over n plus 1 factorial times the maximum of the n plus first derivative on some interval that you care about. So we care about this. If we want to approximate e to the 0.045, we are looking for the maximum of the e to the x on the interval from 0 to 0.45. And so the maximum of the nth derivative, because all of the derivatives of e to the x are e to the x, the maximum will be e to the 0.45. And the c point we have right now is 0. So we have absolute value of x to the n plus first over n plus 1 factorial, actually times e to the 0.45, and instead of x, the x that we care about is 0.045, so we're going to input 0.045 instead of x. And at this point in time, what you can just do is test various values for n, and n equals 4 is the first one that works. So that this value is less than 0.001. So as long as you use 4 terms in your Maclaurin polynomial, the error in approximating e to the 0.045 will be less than 0.001. It may be the case that fewer than 4 terms works, but 4 terms is guaranteed to work. The next unit we discussed was power series, and we found the radius of convergence and interval of convergence for various power series, which basically are these power series define functions, and the function's domain are the set of x's for which the series converges. So to figure out what values of x, for which values of x this series converges, we are going to apply the ratio test. So we'll find the limit as n goes to infinity of negative 1 to the n plus first, x to the n plus first, over n plus 1 the quantity squared, 5 to the n plus 1, multiplied by n squared, 5 to the n, over negative 1 to the n, x to the n. So the negative 1s will absolute value to 1, so we can kind of ignore them. So the limit as n goes to infinity of, so x to the n plus 1 is x to the n times x, n squared 5 to the n, over n squared plus 2n plus 1, 5 to the n times 5, x to the n. And a whole bunch of stuff should cancel. The x to the n's cancel, the 5 to the n's cancel, and we have the limit as n goes to infinity, the absolute value of x over 5 multiplied by n squared over n squared plus 2n plus 1. And that will equal the absolute value of x over 5. And we will have convergence as long as this is less than 1. And if the absolute value of x over 5 is less than 1, that implies that the absolute value of x is less than 5. And that tells me that the radius of convergence, r, is equal to 5. Or one could say that x is in between -5 and 5. Now the one tricky thing here is that when the ratio test gives you a value of 1, it is inconclusive. So your power series may converge at -5 and 5, either one, both, or neither, and we have to actually test those values explicitly to see if the series converges there or not. So let's start by testing x equals -5. So if we input -5 for x, we have the sum from n equals 1 to infinity, -1 to the n, -5 to the n, all over n squared times 5 to the n. So that will be the sum from n equals 1 to infinity, -1 to the n, -1 to the n, 5 to the n, over n squared 5 to the n. The 5 to the n's cancel, and actually so do the -1 to the n's. So we will just have the sum from n equals 1 to infinity 1 over n squared, which actually converges as it's a p-series with p equal to 2. So at x equals -5 we have convergence, and at x equals 5, when we input 5, we get the sum from n equals 1 to infinity, -1 to the n, 5 to the n, over n squared times 5 to the n, which is just -1 to the n over n squared, which also converges by the alternating series test. Or you could show that that series, if you absolute value it, you get 1 over n squared, so therefore this is absolutely convergent and therefore convergent. Anyhow, the interval of convergence is actually -5 to 5, including both endpoints. Let's just do one more example of those. This one is not centered at 0, so it'll look a little bit different. But once again, we're going to apply the ratio test. So we'll find the limit as n goes to infinity of the n plus first divided by the nth term. So x plus 2 to the n plus first over n plus 1 times 4 to the n plus 1 multiplied by n 4 to the n over x plus 2 to the n. So that's going to give us x plus 2 n over n plus 1 times 4. And that will be the same thing as the limit as n goes to infinity of the absolute value of x plus 2 over 4 multiplied by n over n plus 1, which is x plus 2 absolute valued over 4. So as long as that is less than 1, we will have convergence. And that implies that the absolute value of x plus 2 is less than 4. So thus the radius of convergence is 4. And if the absolute value of x plus 4 is less than 2, that implies that -4 is less than x plus 2, which is less than 4, or that -6 is less than x, which is less than 2. So we also need to test x equals -6 and x equals 2. So if we insert x equals -6, that gives us a sum from 1 to infinity. -6 plus 2 is -4, so -4 to the n over n times 4 to the n. So that's the sum from 1 to infinity, negative 1 to the n, 4 to the n, over n times 4 to the n. And the 4 to the n's cancel, leaving us the sum from 1 to infinity, negative 1 to the n over n. And that converges. And just tell me what test you'd use by the alternating series test, the AST. And let's lastly test x equals 2. So when we input 2, 2 plus 2 is 4. So we have the sum from 1 to infinity, 4 to the n over n times 4 to the n, which is just the sum from 1 to infinity, 1 over n, and that series diverges. So we have convergence at negative 6, but not at 2. So the interval of convergence is negative 6 inclusive to not. Let's just do a few more examples. Let's find the interval of convergence for this series. So we have the limit as n goes to infinity. Once again, we're going to apply the ratio test. So the absolute value of n plus 1 factorial x minus 2 to the n plus first over n factorial x minus 2 to the n. So remember that n plus 1 factorial is n plus 1 times n factorial. So I will have n plus 1 multiplied by a singular x minus 2. So this limit of the limit as n goes to infinity of n plus 1 times the absolute value of x minus 2. And this will be infinite so long as x is not equal to 2. So in this case, my radius of convergence is actually 0, and the only point of convergence is x equals 2. Alright, so this one, 3 to the n, so the sum from n equals 1 to infinity, 3 to the n, x minus 2 to the n over n factorial. So once again, we're going to apply the ratio test. A whole lot of ratio tests, you're never going to forget that test. So we'll have the limit as n goes to infinity, so 3 to the n plus 1, x minus 2 to the n plus 1, all over n plus 1 factorial, multiplied by n factorial over 3 to the n, x minus 2 to the n. I've done a lot of this canceling stuff, so I'm going to skip a little bit of steps, a few steps here. So 3 to the n plus 1 over 3 to the n, so this part over that part will just leave us with 3. X minus 2 to the n plus 1 over x minus 2 to the n will just leave us with a singular x minus 2. And then n factorial over n plus 1 factorial is going to leave us with an n plus 1 factorial in the bottom. And that limit is actually going to equal 0, no matter what x is. So that tells us that my radius of convergence r is infinite, since this works for any x, and the interval of convergence is negative infinity to infinity. So after discussing power series, we moved on to representing certain functions by power series. And when we began this, pretty much all of our representations relied on the geometric series sum formula. So the fact that the sum from 0 to infinity, a r to the n, was equal to a over 1 minus r, and is convergent as long as the absolute value of r is less than 1. So, for example, for f of x here, we can think about f of x as x squared times 1 over 1 plus x. And 1 over 1 plus x can be thought of as 1 over 1 minus negative x, which can then be expressed as a sum from 0 to infinity. So using the geometric series formula, the a in this case is 1, and the r is negative x. So negative x to the nth, which is the same thing as the sum from 0 to infinity, negative 1 to the n, x to the n. And this will converge as long as the absolute value of negative x, which is just x, is less than 1, giving me radius of convergence 1. Now so far that's just the power series for the 1 over 1 plus x portion. To find the power series for f of x, we have to take x squared multiplied by 1 over 1 plus x. So x squared multiplied by the sum from 0 to infinity, negative 1 to the n, x to the n. So we have the sum from 0 to infinity, negative 1 to the n, x to the n times x squared. And that's the same thing as the sum from 0 to infinity, negative 1 to the n, x to the n plus second power. Another technique to find a power series representation of a function was to use a derivative or an integral somehow and integrate a power series. So for this example, notice that the derivative of ln of 1 minus x is equal to negative 1 over 1 minus x. And we know how to find a power series for this. We could use a equals negative 1 and x equal to r. And so this tells us that if we integrate negative 1 over 1 minus x, we will have a power series representation for ln of 1 minus x. So we have that ln of 1 minus x will equal the integral of negative 1 over 1 minus x. So a power series representation for negative 1 over 1 minus x would be a sum from 0 to infinity, negative 1, x to the n, dx. And now antidifferentiating, we antidifferentiate term by term, and we'll have negative 1 x to the n plus first divided by n plus 1, and that's it. So that's the power series representation for ln of 1 minus x. This power series obtained by integrating has the same radius of convergence as the power series that you integrated. So this one converges if the absolute value of x is less than 1, so it has radius of convergence 1. One thing that can change, however, is the interval of convergence. That may be and often is different for a series obtained by integrating another power series. Alright, find the power series centered at c equals 0 for this function. So if we're going to use the geometric series formula, we have to have 1 minus a number. So we have to take this f of x and factor out that 8. So that'll be 8 times 1 plus x over 8. And this 4 over 8 can really reduce to just 1/2. So we'll have 1/2 divided by 1 minus negative x over 8. And now we can use the fact that a over 1 minus r is equal to a sum from 0 to infinity a r to the n. So this will be expressed as a sum from 0 to infinity 1/2 negative x over 8 to the n. Zero to infinity. Okay, so we'll have negative 1 to the n, 1/2 x to the n over 8 to the n. And just so you're aware, notice that 8 to the n is the same thing as 2 cubed to the n, or 2 to the 3n. So I can write this as the sum from 0 to infinity, negative 1 to the n, 1/2 times x to the n over 2 to the 3n. And then these two actually can be written as 2 to the 3n plus 1. So sum 0 to infinity, negative 1 to the n, x to the n, 2 to the 3n plus 1. It's helpful to know how these simplify sometimes, just in case you're checking your answers against the back of a book if you're using your textbook to do some extra practice. I didn't ask for radius of convergence, but I think I forgot to. So this will converge as long as the absolute value of negative x over 8 is less than 1, which means the absolute value of x is less than 8. Hence, the radius of convergence r is equal to 8. Find the power series for f of x equals 1 over x centered at c equals 1. So here we have to take 1 over x, and it has to somehow contain x minus 1. So to do that, we will have to have 1 plus, add 1 plus in the denominator to compensate, so we still have a representation for 1 over x. And then to use the geometric series formula, I have to make that into negative x minus 1. So now I can express this as a sum from 0 to infinity, negative x minus 1 to the n, which is the same thing as the sum from 0 to infinity, negative 1 to the n, x minus 1 to the n. And this will converge so long as the absolute value of x minus 1 is less than 1, so it has radius of convergence 1 also. So all of this relied on the fact that you could somehow manipulate your function into being of the form 1 over 1 minus a number somehow, or something that times a constant or something. So in the next section we discussed how one finds power series representations for all sorts of functions using Taylor and Maclaurin series. So first of all, here are some common Taylor and Maclaurin series for various functions that you should know. So 1 over 1 minus x, this is the geometric series. So that's the sum from 0 to infinity, x to the n. It has interval of convergence, negative 1 less than x, which is less than 1. E to the x is given by 1 plus x squared over 2 factorial plus x cubed over 3 factorial, or written in summation notation, 0 to infinity x to the n over n factorial. This has interval of convergence negative infinity to infinity. Sine x's Maclaurin series is given by x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus plus etc. So as a infinite sum, it's written as negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. And then cosine's Maclaurin series is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus etc. So sum from 0 to infinity, negative 1 to the n x to the 2n over 2n factorial. And the last one was inverse tangent. This one was found using the fact that the derivative of inverse tangent is 1 over 1 plus x squared. And you had to integrate 1 over 1 plus x squared to get inverse tangent of x. And that is given as a sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1, no factorial. And it has interval of convergence negative 1 to 1, including both negative 1 and positive 1. So in general, let's find the Taylor series for sine at pi 6. So we're not going to use any of the previous things we wrote down because those are Maclaurin series. So the form of a Taylor series centered at pi 6 will be f of x equals f of pi 6 plus f prime of pi 6 times x minus 6 plus the second derivative at pi 6 over 2 factorial times x minus pi over 6 squared plus the third derivative at pi 6 over 3 factorial times x minus pi 6 cubed, etc. So first we're going to need multiple derivatives of sine at pi 6. So first of all, f of pi over 6, that's sine of pi over 6, which is root 3 over 2. F prime of pi over 6, that will be cosine of pi over 6, which will be 1/2. The second derivative will be negative sine, so negative sine of pi 6 will be negative root 3 over 2. And the third derivative at pi 6 will be given by negative cosine of pi 6, which will be negative 1/2. So using that, my Taylor series will be f of pi 6 is root 3 over 2 plus 1/2 times x minus pi over 6 minus, well, plus negative root 3 over 2 divided by 2 factorial times x minus pi over 6 squared, and then minus 1/2 over 3 factorial x minus pi over 6 cubed. It gets pretty icky. So here we go. It's root 3 over 2 plus 1/2 times x minus pi over 6, and then minus root 3 over 2 times 2 factorial x minus pi over 6 squared, and then minus 1 over 2 times 3 factorial x minus pi over 6 cubed. So I don't accept, and this pattern is going to actively, actually flip-flop. So the next term will be positive root 3 over 2 times 4, and with positive root 3 over 2, positive root 3 over 2 times 4 factorial x minus pi 6 to the 4th. Just show me that the pattern continues. There's no great way to write this in summation notation, so if I were to ask you, I'd probably just ask for the Taylor polynomial, and I would give you a place to truncate it as opposed to the series. One common method of constructing Maclaurin series is to use a given Maclaurin series and input a different value, or multiply them together, or multiply one of them by a variable, or some combination of those things. So for this, we have to know that inverse tangent is given as a sum from 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1. And I have inverse tangent of x cubed, so I'm going to input x cubed. So that will equal a sum from 0 to infinity, negative 1 to the n, x cubed to the 2n plus 1, all over 2n plus 1. And because inverse tangent has radius of convergence 1, this will converge if the absolute value of x cubed is less than 1, which implies that the absolute value of x is also less than 1, and it has radius of convergence 1. Now these exponents will multiply, and I have a sum from 0 to infinity, negative 1 to the n, x to the 6n plus 3 divided by 2n plus 1. So So that is the Maclaurin series for inverse tangent of x cubed. Alright, here we have x times e to the 3x. So recall that the Maclaurin series for e to the x is the sum from 0 to infinity x to the n over n factorial, and that has radius of convergence r equal infinity. So we can write this as x times the sum from 0 to infinity 3x to the n over n factorial, which is the same thing as x times the sum from 0 to infinity 3 to the n x to the n over n factorial. And when I bring that x inside the sum, I will now have x to the n plus 1 instead of x to the n. So the power series for x times e to the 3x is the sum from 0 to infinity, 3 to the n, x to the n plus 1 over n factorial. And recall that x to the n times x to the first, that's where that x to the n plus 1 came from. Alright, sine of x to the fourth. So you have to first recall what the Maclaurin series is for sine of x. So we know that sine of x is equal to a sum from 0 to infinity, negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. And so we'll input x to the fourth. And this has radius of convergence infinity, so inputting x to the fourth will not change that. So we have a sum from 0 to infinity, negative 1 to the n, x to the fourth to the 2n plus 1, all over 2n plus 1 factorial. So negative 1 to the n, that would be x to the 8n plus 4, all over 2n plus 1 factorial. Right, 10 to the x doesn't seem like something immediately obvious where we can work this out, but we have a formula for e to the x. There must be some way to make this work. So notice this, is you can write 10 as e to the ln of 10, which is the same thing as e to the ln 10 times x. So I have the formula for e to the x equals the sum from 0 to infinity x to the n over n factorial. What I'm going to do here is input ln 10x for the x. So that will give me a sum from 0 to infinity ln 10 times x all to the n over n factorial, which is the same thing if you want to write it as 0 to infinity ln of 10 to the nth. I mean, ln of 10 is just some weird irrational number, so no big deal. X to the n over n factorial. That was a little bit tricky. I don't think that will be on your nothing like that will exactly be on your test, but good to know. So one application of infinite series is to find integrals that we cannot find using other methods. So e to the x, notice, is 1 plus x squared over 2 factorial plus x to the third over 3 factorial, etc., all divided by x. So dividing every term by x gives us 1 over x plus 1 plus x over 2 factorial plus x squared over 3 factorial plus x to the third over 4 factorial, etc. And if we integrate term by term, the integral of 1 over x is ln x, absolute value x, plus x squared over 2 times 2 factorial plus x to the third over 3 times 3 factorial plus x to the fourth over 4 times 4 factorial, etc. And other than, I can't express this ln x in the sum, but this stuff I could write in an infinite sum form. So this would be ln absolute value of x plus a sum from n equals 1 to infinity, x to the n, over n times n factorial. So there is the value, or a power series representation of the function that is the antiderivative of e to the x over x. I'm not saying I know what function that is, or if it even really has a name, but that is the antiderivative of e to the x over x. And one final application is one can always also use a series to evaluate limits. We can also use this find this limit using Lhopitals, which we will use to check our series method. So notice that sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. Lots of stuff, dot dot dot. Okay, minus x all over x cubed. So taking away x, this first x and last x cancel. Now I just have everything divided by x cubed, and that will reduce all the powers of everything in the numerator by 2. So my first term will now be negative 1 over 3 factorial plus x squared over 5 factorial minus x to the 4th over 7 factorial. The point being, past that x squared over 5 factorial, every single term has an x. Now you can input, in the numerator that is, and now you can input 0. Every single term past the 1 over 3 factorial will zero out. So this limit is just going to be negative 1 over 3 factorial, which is negative 1/6. Now just to verify, you also could have used Lhopitals rule. So find the limit as x goes to 0, sine x minus x over x cubed. So this limit is of the form 0 over 0. So you apply Lhopitals rule, and we have the limit as x goes to 0, cosine of x minus 1 over 3x squared. And we can apply Lhopitals rule again because this limit is still of the form 0 over 0. So cosine's derivative is negative sine, 1's derivative is 0 over 6x, and still 0 over 0. So one more application of Lhopitals rule. We get negative cosine x over 6, and now we can input 0 and we also get negative 1/6. So both methods yield the same limit. There are just two different methods used to find this limit. So series is also an option if you're finding a limit.